Luciano Campi from LSE, and he will talk about mean-field games. Please.
Thank you. Well, thank you very much for the invitation. I will be talking about this project with Markus Fischer from Padua University. And this is about n-player games and mean-field games with absorption. So this is the outline on the top. So there will be like short introduction, and then I will talk about the setting of n-player games with absorption, and then the associated mean-field game, which is supposed to be like the game, the limit game associated to this n-player games here. And then I will be talking about one of the main results we have, which is actually that under some non-degeneracy assumption, you can actually take the solution of the mean-field game and use it as an approximation to construct actually the Nash equilibrium for the n-player game. And then I will give you a counterexample showing that actually if the in case of degeneracy, so if actually the diffusion coefficient is 0, well actually in this case you can have an example where actually the limit, the mean-field game solution is not a good approximation of the prelimit game. Okay. And then there will be some conclusions here. Okay. So this is just a brief introduction. So this class of games here, mean-field games, has been introduced simultaneously by Lastilios 2006 and Juan Keynes-Balamet the same year, coming from two different backgrounds. Actually, Lastilios, of course, they come from analysis, while actually Juan Keynes-Balamet from more mathematics applied to engineering. Okay. And the main idea is that actually you imagine that you are interested in some n-player game, which is symmetric, so actually the players can be exchanged. Okay. And you are interested in solving this game, for example, in finding the Nash equilibrium. And so these players, they interact, but they interact only in a weak sense, in a sense that actually they interact only through their average behavior. So each player is interacting only with the average behavior of the other players, not with any other players separately. Okay. So let's say that this is probably very difficult to solve because n can be very large, right? So actually what you do, you pass through the limits when n goes to infinity. And this converges in some sense to a one-player game interacting with the theoretical distribution of the population. Okay? And this is of course linked to this phenomenon that has been very well studied in probability, which is called propagation of chaos, which corresponds to kind of low large number. Okay? So maybe I can show you very briefly actually how this works. So what you have here is that imagine you have an agent from 1 to n, and you have like a state variable which is one-dimensional, but you have one evolution for any player. So you have something like this. So imagine that this is a kind of this is like homogeneous diffusions, and then here you have the x bar t dt, and then here you have some noise. Okay. The thing is that these Brownian motions are independent, okay? And here you see the interactions happens only through this x bar. X bar is the empirical mean, okay? So x bar is just the sum from 1 to n of the coordinate here. So here in principle what you can do is that you can use the low large number here, okay? So this guy is actually converging for the low large number to the expectation of some xt here, okay? Where actually the xt would follow this kind of dynamics here. So b xt, here you have convergence to the mean, so you replace this with the expectation, and then you have actually you just have w here, okay, one w. So you have convergence in some sense to this guy to this guy here, okay? And mean-field games means actually you are adding controls here. Okay, so here you are just introducing one control variable here. Okay, but what you get, of course, actually every agent wants to minimize some functional, and when you pass to the limit, you will get some minimization problem where actually now the state variable follows this dynamics with the control appearing here. Okay. Okay, so this is the main idea, and then what you do, you use the control that you find here in the limit problem to actually define some approximate Nash equilibria for the prelimit. Okay. So this is the main idea, and actually one of the main results here in mean-field game is that all this procedure works, and even if the volatility, even if the coefficient sigma is 0, it still works, okay, in this setting. And this is a finite horizon setting, so the problem is between 0 and capital T, okay. So you can actually follow this kind of approach, okay. So here's some literature. So you have the following recipe, which is suggested by exactly what I was showing here. So you pass through the limit first, so you get the problem with this limit dynamics here. You study the equilibrium in the linear particular solution of the limit problem, and then you use those equilibrium to construct approximation for the prelimit problem. Okay. You can do this using many different approaches here. So of course the original one is the one using PDEs that was actually initiated by Lasrillions, Cardaliaguet, Ashlou, and others. Okay. This is a very well developed field now. And now recently, a few years ago actually, this new probabilistic approach started due to René Carmona and students and co-authors. So in particular, to Alain de Soussan, Carmona, Delarue, Kolokoltsov, Laker, Yam, and others. Okay. And I think this is a very flexible framework because you can actually fit many applications into this kind of, as soon as you have a very large populations of agents interacting, so this can be applied to economics, finance, to crowd dynamics, and so on. Even in engineering, you have a lot of application of this kind of models. Okay. And actually, very recent, if you want to have like an idea, general idea of the overall approach, there is a very recent book by, actually it's not forthcoming anymore, it's just appeared, by René Carmona. Okay. Or you can watch this Lasrillions recordings at Collège de France. This is more demanding. Okay. So, the main results that we have, so we consider a system of weakly interacting. Weakly interacting means actually they are interacting through this average behavior. Control diffusions. This is the novelty here, which are stopped as soon as they exit a given set. Okay. So this is what I mean by mean-field games with absorption. And under some technical assumption, for example, this is the main one actually, non-degeneracy of the diffusion coefficient. We have the existence of a feedback solution for the mean-field game. And we have also that limit solution to the mean-field game actually is nearly optimal, so it's nearly Nash equilibrium for the prelimit and player games. And then we have a counterexample showing that in the degenerate case you cannot use the limit solution as an approximation for the prelimit. Okay. This counterexample is funny because actually depends on the audience actually, because I know that my co-author Markus once presented it in front of an audience of experts in deterministic control, and for them it was quite obvious to have this kind of counterexample. They were more surprised by the fact that the Dida-Bragnian motion actually add regularity to the problem. So it depends on the audience. Some related works. These are works with no actually control feature. So there is this work by Gizekis, Peliopoulos, over Sirignano, that actually there are 3 papers by them, and they look at mean-field models, so without the control part, for portfolios of credit derivatives. So they want to study what happens to the losses when the size of the portfolio is very large. There is this very recent paper by Hamlin Ledger on Mekin-Vlasov. Mekin-Vlasov is very related actually to this kind of dynamics here with absorption, but they use a very completely different approach, and they are also motivated by some default risk modeling. And also there are a couple of papers by Delarue, Dubertaler, and Tandre, but they are more, it's somehow related, not exactly the same model, but they are motivated by application to neurology. And none of them actually have the control. So this is the main difference. Okay? But even if you drop the control from our approach, you will still feel there are some differences actually between what we do and the models that they do. Okay, so let me first of all describe the n-player dynamics. So here you have n players, you have some finite horizon capital T, you have some set gamma, which is a set of control actions, and then you have the set O, which is a set of non-absorbed state. Okay, so actually the state variable, they are already in O, and then when they touch the boundary of O, actually they will be killed. Okay. So given a vector U, which is a vector of gamma-valued progressive feedback strategies, okay, so you can define the evolution of the player states in this way through this equation. So here you have the initial value. So this is for n is fixed, the number of players is fixed. This is the dynamics for the ith player. The initial condition, you have some noise, independent noise, okay? Every player has his own noise. And yes, you have this drift here. So this is like a drift, which depends on time and depends actually on this pi n, which is, I will show you here, but pi n is the conditional empirical distribution of the x. Okay. So this is fixed, and then you have the control, which is additive. Okay. So when I say actually here progressive control, it means actually the control depends on time and depends on the path of x, but only in a progressive way. Okay. So from 0 to s. Right, so W1, Wn are independent in the processes, sigma is a matrix, and B bar and W0 are given functions, and so this W0 is just some weight function, okay? And pi n is a conditional empirical measure of the states of the players still in this set of at time t. It is defined in this way, okay? So this is counting the number of players which are still in O, and then you are divided by the number of players which are still alive at time t. Okay. Okay, right. So this tau here is just the first time that actually each state xjn exit the set of. Okay. And then you have some kind of initial distribution here, which is fixed and is given by this low un. Okay, and you assume that since you don't want to break the symmetry here, you assume that the initial low is also fixed. It's also symmetric. Okay, right. So of course, all these players they will be minimizing some functional. Okay. So un here will be denoting the set of all gamma value progressively measurable processes, and unfb is a set of all strategy vectors in a feedback form, but such that equation 2, 1, which is this equation here, has a unique solution in distribution. So player I will evaluate every strategy using this functional here. So it's minimizing. He wants to minimize this functional here. So you have some running cost, okay, from 0 to this first exit time. Okay, running cost f, which depends again on time, on the private state of the agent, of the player, on the conditional distribution through this weight w1, and then also on the strategy. Okay, and then you can have some final cost here, which depends on the terminal time and the terminal state. Right, so this tau in appearing here is the final time horizon, which is just the minimum between this fixed time horizon capital T and this exit time. Okay. Right, and this pi n again as before is just a conditional distribution induced by the private states. Okay, so we need some assumptions. These assumptions are not minimal, but I mean I guess that they can be of course generalized, but here I mean the point we wanted just to stress what happened in the presence of this absorbed set. So I think there's no really point here to be very, very general, at least not for now. So first of all, we assume that these functions here, the weights, the drift B bar, the running cost, the terminal cost, they are actually bounded and measurable. Okay. Then you assume some continuity here for the weights, the terminal cost, assume that it is continuous. You assume that actually the running cost is also continuous for fixed T and uniformly. Lipschitz continuity for the drift, and then you assume that the action space, the gamma here is compact, non-empty, and then the state space is set O is actually also non-empty, it is open, and also the boundary is regular. Okay. You need actually this regularity of the boundary because at some point you will be using the regularity of the dependence of the exit time from the initial condition. So that's why you need somehow the regularity of the boundary of this set O. And then we will also need, not everywhere, but in the main result, yes, actually in the approximation result we will need this assumption. We assume that the matrix sigma has full rank. And under this non-degenerate assumption, you can prove that actually for any feedback strategy you have exists in the uniqueness law of the sigma. Okay. Now, what about, okay, then you would like, of course, to study the Nash equilibrium in this setting of this n-player game. So here we use this notation which is standard in game theory. So we say that given a strategy vector u and given an individual strategy b here, we'll be using this notation. U minus I denotes actually the strategies of all the players but I. And here V is just the strategy of player I, which is different than the UI here. So you're replacing UI with the strategy V. Okay, this is just one notation, which is very standard in game theory. Okay, so the definition of Nash equilibrium is the standard one. So you fix an epsilon here. You say the strategy vector U is an epsilon Nash equilibrium for the n-player game if actually for any player I and for any possible deviation B from the strategy U, you have this inequality here. So what you get with the strategy U is actually smaller than what you can get by deviating plus some epsilon. Okay. You are minimizing, right? So it means actually maybe you can improve but very little, only by an epsilon. And of course, this epsilon is zero, meaning actually you cannot improve just by deviating, which is the standard notion of Nash equilibrium. Okay. And here we are looking at Nash equilibrium with full information, so everybody knows about everything here. Okay. And feedback form strategies. Okay. Okay, so this is the description of the n-player games. So now I have to give you the description of the limit of the mean-field game that you have at the limit. So here you will have this SDE now, so you have XD with some initial condition, some drift, which is the same drift as before, same integral with the same weight W0, which is now integrated with respect to this measure P. Of course, I have to tell you what this measure is. Okay. And then you have the same nodes as before. Okay. So here P, for the moment, it's just a flow of probability measures. Okay. Because it's going to be like you will have just the limit of this sequence of conditional empirical distributions. Okay, so the limit will be like a flow of measure. Okay. So for the moment, let's be generic here. I will just use a generic element of this set here. U is a control, okay, and W is just the dimensional limiter process. Right. So actually, since we know what we want to do, I mean, we are trying to find like a limit problem which somehow is related to the n-player games. So this P, we expect this P to be the limit of this conditional empirical measure. So we expect this P to be actually the conditional distribution of the state X. Okay? So in view of the n-player game, P should correspond to the flow of conditional probabilities of X. Okay? So this is what we would expect. Okay, so now what about the problem, the minimization problem here? So again, here UFB is the set of all feedback strategies, such that the previous equation has a unique solution in below, and given an initial distribution, and the cost associated now to this strategy is given by this. Okay, so you have the same running cost as before, depending again on S, on the state, on private state, on this weighted integral of this measure P, the flow measure P, the control, and then you have the same terminal cost as before. Okay, the function F. Well, X is the solution to the previous SD with initial distribution nu, and tau here, tau is just the minimum between this finite horizon capital T and this tau X. Tau X is the first exit time from O of the process X. Okay. Okay, and this is now the problem that we want to solve at the limit. So it's a minimization problem of this functional here. And now the minimization, this problem now has to be understood in a weak sense. So I'm minimizing with respect to all filter probability spaces, initial conditions, control, alpha, and Brownian motions admissible in some sense, such that actually the initial law is given exactly by the law I fixed. Okay, so this is just a weak formulation of the minimization problem. And of course, if I'm minimizing like this, of course I will get something in principle smaller. Okay, so this V here, which is a value function corresponding to this problem, is going to be smaller than the minimization problem with respect to the feedback strategies only. So in the strong form. Okay, but we were assuming something more. So under our assumption, it can be proved that actually you have equality here. Okay. So you can use actually the weak formulation, which is actually nice because you can use some martingale problems there. Okay, so what's the definition of the solution of a mean-field game here? So a feedback solution of the mean-field game is a triple, initial law, control, and flow measure, okay, such that mu is a probability distribution with a support in O, U is just some feedback control, and P with some flow measure such that optimality is satisfied. Okay. And such that you have this is the important property here, that the conditional mean field property, meaning that actually P has to be the conditional distribution of X. So it's the distribution of X conditioned to stay in O at time T. Okay? So this is the mean field condition that you would expect. Okay. Right. Of course, for every T such that this probability is positive. Okay, so this is not the notion of solution in this mean field game. So now, what we want to do, we want to check if actually, if I take a solution of the mean field game, I can use this to build actually an approximate Nash equilibrium for the n-player games, which is actually the problem I'm definitely interested in. Okay. So X here denotes the set of all continuous paths. Nu is the initial distribution, and theta n is just the law of this Brownian motion with some diffusion coefficient and some initial value psi. Okay, so the theorem is claimed basically that if you assume non-degeneracy, so if this matrix sigma is has full rank, and then of course you assume all the assumptions that actually assumed before, suppose that nu n is nu chaotic. Nu chaotic means that actually is converging, is like kind of low Blatch number here for the initial laws. Okay, so this sequence of laws is actually converging to some limit low nu. Okay. Now, if you assume that nu up is a feedback solution of the field game, as in the previous definition, which is regular, in the sense that actually all sense that this measure here, this law, is concentrated on path where actually the control is continuous. Okay, so this is said in a different way. This is just saying that actually where U is continuous, the probability is 0. Okay, so if you assume that the solution of the mean field game is concentrated where actually the control is continuous, okay, and actually I will show you later, but you can have assumption guaranteeing this that the property is true. In this case, you can take the solution of the mean field game U, and you can define these strategies for the n-player game. So the strategy of player I, at time t, and when the path is phi, is defined in this way. So you take the solution of the mean field game at time t, and you plug phi I. Okay, phi I. So it's just the coordinate of this the state process referring to player I. So basically, the player are using only their own private states to build the equilibrium. Okay, they don't have to use the state variable coming from the other players. They are just observing their own private states, and this is enough for them to actually build a Nash equilibrium. Okay, so this gives a sequence of approximate Nash equilibrium in the sense that for all epsilon, there exists some n0 large enough, such that un built in this way is an epsilon Nash equilibrium for the n-player games, where actually n is bigger than this threshold n0. Okay, and this assumption here is very important in the degeneracy. Okay, so maybe I don't know how much time do I have, maybe I can skip the proof of, yeah, probably. It's a good idea to skip this. Okay, maybe if I have time I can come back to this proof later, but so let me go to the second result that we have. So, what we have here is an existent result, of course, because the previous theory is based on the existence of a solution for the mean field game, so we need to, of course, we need to prove existence of the solution. So we assume that actually we assume some additional hypothesis here. We assume that this function is a Young minimizer. So this is the running cost, and this is some z plus gamma. This comes from considering the Hamiltonian. Okay, the Hamiltonian associated to the minimization problem. Okay, so that's why, because here in this theorem, okay, I will just sketch the proof a little bit, but what we are using here, we are just using GSD methods, contracting maximum principle, so we will need some regularity assumptions on the Hamiltonian here. Okay, so that's why we need this assumption. So these functions here as a Young minimizer given LET, x, z, and mu, plus some mild technical assumptions. Then in this case, there exists a feedback solution of the mean field game, so initial law, control, and flow of measure, T, such that actually u t phi is just any generic path, okay, is equal to u tilde t phi t. So actually this is not just feedback, it's going to be Markovian, okay, and it's going to be actually a smooth solution, because this function u tilde is a continuous function. Okay. And And this is actually, even the continuity is very useful because in the approximation result. The approximation, you need a lot of continuity actually, not just of the control, but also of the exit time. Okay, so that's why actually you're assuming the regularity of the boundary of the set O, and that's why actually you really need this continuity here in order to prove the approximation result. And the proof is based on like these steps here. So you first fix the flow P. Okay, and then you prove that for any fixed flow of measure P, there exists some optimal feedback control. And here you can use some Pontryagin maximum principle based on BSD techniques. But here the BSD has a random terminal time, right? So you need to use some results due to Darling-Purdue 97, where actually they look at BSD with random horizon. And then for the regularity, you pass from the BSD to the associated PDE, and then you use some PDE techniques to get the continuity of the control. Okay? And actually here we adopted some results that we taken from Fleming-Richel book, okay, which is based on Zetskalia book on regularity. Yeah. Right, so this is very important, as I said before, for the approximation results. And now, of course, now you proved regularity, you proved existence when the flow of measure is fixed, but now you want this flow of measure to be equal to the conditional distribution of the process. So it is exactly there that actually you need to use some fixed point argument. Okay. So for the mean field condition, you apply Schauder fixed point, and this actually is very much in the spirit of this paper by Carbona and Laker, 2015, to a suitable map. And this, of course, in order to apply this fixed theory, you have to prove that this map has some continuity properties again. And for this, it's very useful, actually, what is very useful is some stability results of BSD with random horizon that has been actually proved in this paper by Dorion. Okay. So these are the techniques that we use for the existence. Now, I have time to talk a little bit about this, the counterexample. So, the counterexample is dimension 3. Okay, so you have 3 variables here. Time horizon is 2, and then we assume that we are in the degenerate case, so sigma is actually 0. Okay. So the only randomness in this counterexample is coming from the initial conditions. Okay. Initial distribution, so you have 3 coordinates, so the initial distribution of the first 2 coordinates is just given by rho, which is Rademacher distribution, so it's -1 + 1, probability 1/2, 1/2. And the third coordinate is just 0 at the beginning. Okay. And then you have this set of control actions, which is given by the first coordinate. So you cannot control the second and the third coordinate, you can control only the first one. Okay. And then you have the set of non-absorbing set, which is this set here. So, but maybe I can draw a picture. It's something like this. Well, it's not smooth, as you can see from the definition, but actually it can be made smooth. Okay, but and it works the same actually, the counterexample. So here you have something like this. This is basically the section of this set on the plane x1, x3, okay, and then you have something like this here. You have something like this in dimension 3. Okay, so you have a kink here. Okay, so this is the shape of the set. And now, what about the dynamics of this X process? So you have, you have this drift here. So this is the drift of the first coordinate. So it's minus absolute value of y, which is bounded. Here, you know, this bounded at 0 is due because we want this actually to fit our assumptions. Okay, so that's why actually we truncated this at 1/4. 0, so the drift for the second component, and just 1 drift equal to 1. So the third component starts from 0 and then it goes up as t. Then we have some cost coefficients here, so the running cost is just identically equal to 1, and then the terminal cost is given by this expression here. It's 1 plus x3 times, so this is the product between first and third coordinate divided by 12. I mean, all these numbers here, 12 and 1/4 and so on, and they are have been chosen in a way that actually all the assumptions in our setting are satisfied. So in particular, this capital F is always positive, even small f is going to be positive, and so on. So the constants are really chosen just to to fit the framework that we have. Okay, so if we sum up all this, so the dynamics of the x processes are given by these equations here. So this is the first coordinate, initial value, control, and then this is the drift. So the drift here, you have this term here, which depends only on the second coordinate, okay, for any player. The second coordinate is just identically equal to the initial distribution, so it's always constant. The third coordinate starts at 0 and then increase as t. Okay, right. So here we can do some calculation here, very, very easy. You can prove that actually xi is always bounded from above by 1 plus t, and from below by minus 1, minus 3 over 2 times t. Okay. So you get, from here, you can get actually xi can leave all before 2 only if actually this is going to be equal to 2. Which is possible only if this guy is actually 0. Okay? But the probability of this event is actually 0 if n is odd, because this is just random variables plus 1 minus 1. Okay? So here in this case, the exit time is just equal to 2. Okay? And the cost for player I is given by this expression here. We just plug the function that I've chosen before. Okay? And you can prove that the Nash equilibrium in this case is just such that every agent is choosing minus 1. Okay? Right, so you can compute everything explicitly here for the player games. Okay. So now, what about the limit? The limit, we have this dynamics here. So the first coordinate is like initial value. He has a control here, and then the same drift as before, with this weighted empirical. This is weighted measure here. Okay, weighted flow of measures. Second coordinate is always equal to its initial condition, so you have it like 0 here. Third coordinate is just identically equal to t. Okay. And now assume that you have some flow measure p with a good support, and assume for the moment that actually this is 0 here. Okay. Then the dynamics is going to be simpler, so you just have for the first coordinate psi1 initial value plus just the integral of the control. And then here for the second and the third, the same as before. Okay. And the cost in this case is just given by this expression. Okay, so you can just pick the small f and the capital F as before, you just check and then you get exactly this. So you are minimizing the exit time basically here, plus 1. This 1 doesn't really matter, it's there just because I want this thing to be positive. Okay? But it really doesn't matter. And then you have again this exit time. Again, this 12 again is not really important here. Times the first coordinate. Okay. And imagine you take this control now. So you pick 1 for the first coordinate, that's 0, 0. If the initial value of the first coordinate is 1, and t is between 0 and 1, otherwise you take minus 1. Okay. So this is your control. And actually, this is exactly the minimizer. Okay. So you can do some calculation and you can find that actually this is the minimizer. X is the unique solution of the equation 5.1 under such a control, and actually under such and then set this by star. By star now is the conditional distribution of x. Okay. So you can check that under this control, the p star here has the good support, so the support is contained in the closure of O, but especially you have this condition here which is satisfied, which is exactly the condition you started from. Okay. So this is coherent actually, the condition we assumed in the beginning. I mean it's one slide before. Okay. Right, so define now, you start from here, you can define a fit-based strategy, you start, just starting from this strategy here. In this way, you start t phi is just equal to this vector, so 1, 0, 0, if the initial condition is 1, and t is before 1, or you do minus 1 in case the initial condition is minus 1, okay? And then, when t is actually, in case the initial condition is 1 and t is bigger than 1, you do whatever you want, it's okay. Doesn't really matter. Okay, and you can prove that actually this gives you a fit-based solution of the infinite game. This new u star and p star. Okay, so p star is really the conditional distribution, u star is defined in this way, and u is just the distribution that I fixed in the beginning. Okay, right, but now let's implement